Welcome back. This is our last unit of this year. We're looking at Unit 3, rational functions. So there will be two lessons on this unit. We are actually going to skip 3.1. We are going to 3.2 directly, okay? So we're talking about rational functions here. So I guess first of all, we need to define what a rational function is. Okay, so a rational function has a form of y of x equals to, so this is the, I'm going to call r of x. Rational function r of x is equal to f of x divided by g of x, where both f of x and g of x are polynomial functions. Okay, so they are both polynomial functions. So it'll be like quadratics, cubic functions, fourth degree function quartic, fifth degree quintic functions, and so on. Sixth degree linear functions. Okay, so even constant, they are also polynomial functions. Okay, so as long as both the numerator and denominator are polynomial functions, then the division, okay, of those two would be the quotient, and that is the rational function. Okay. Non-permissible values. So non-permissible values are the values that are not defined in the domain. Okay, so I guess, if it's a rational function, remember it's a fraction. So then what makes it undefined is when the numerator gives you a 0, right? When the numerator is 0, you cannot divide it by 0, therefore that is undefined. So that's what we call the non-permissible values. So the values that will make r of x, so this rational function, undefined. So these are non-permissible values. Okay, so you can see here it says non-permissible values of f of x. Okay, so I should say this is r of x, I guess. So the function, okay, it doesn't matter. Create vertical asymptotes or holes on the graph. So we've seen vertical asymptotes, right? Vertical asymptotes are like an imaginary vertical line that the graph will not cross. Holes we haven't seen. Okay, so we will see actually in the next example right here. You can see here's the graph for f of x. Okay, so this is the rational function, and right here this is the hole. Okay, well, here's the question, I guess. It says a vertical asymptote is at, so here's the vertical asymptote. I think you can see it's right here. So vertical asymptote would be the non-permissible values here. So you can see from this expression, this rational function here, the non-permissible values would be x equals to 2 and x equals to -5. Now, this vertical asymptote, I think it's quite clear. It's the -5, not the +2, right? So this happens at -5. That vertical line, imagine the vertical line is the vertical asymptote. We do have a hole here as well, right? Right here at that point. We know the x coordinate is a 2. So it's happening at x equals to 2. But we are also interested in finding out what the y value is. Okay, so you cannot quite tell what the y value is on this graph. But really, if you take this expression and simplify it, okay, I'm going to copy it down first. If you simplify it, you can actually cancel the x minus 2. So they actually just reduce, right? They just cancel themselves, okay? So you end up with x minus 3 over x plus 5. Okay, so now to find a y value, all we need to do is plug in this x value of 2 in here. So then f of 2 would equal to 2 minus 3 divided by 2 plus 5, which is -1 out of 7. And that is, -1 out of 7. That is the y coordinate of this hole. Okay, so that's how you find the coordinates of this hole. So whatever that is being cancelled or reduced would become the hole. And whatever that's not reduced or cancelled, that remained here, right? You can see x plus 5 remains here. That would actually create the vertical asymptote. Okay, so here it says holes in the graph occur at point x equals to a if x minus a is a factor of the numerator. I don't know why I didn't leave that much space. Numerator and denominator. Okay, so if it's a factor of both numerator and denominator, then they'll cancel out, therefore it creates the whole. A graph has a vertical asymptote if x minus a is a factor of the denominator. So you can see the right, x plus 5, right? That's a factor. So it's a factor of the denominator, but not a factor of numerator. Okay, you can see there's no x plus 5 on the top right there, and therefore that gives you the vertical asymptote. Okay, so here are 3 examples. Let's quickly take a look and see what we actually have here. Okay, so for A, you can see we actually do have a hole. Okay, because the x minus 2 and the x minus 2 will cancel out. Okay, part B, there is going to be, so this will cancel out with that one. Okay, so this is interesting. One of the x minus 2 got canceled out, but we still have one remaining. So do we actually have a hole, or do we have an asymptote, or do we actually have both? Okay, well, if you think about it, hole is something that the graph doesn't go through, and that's kind of the same idea as the vertical asymptote, right? So vertical asymptote means the graph does not go through that vertical line. So actually, if we say that's a vertical asymptote, it kind of covers the whole part, right? So we would say there's going to be a vertical asymptote. Okay, vertical asymptote. Okay, for part C, let's see. Okay, so this one is also interesting. This is x plus 2. That is negative 2 minus x. I think we've seen this many times. We could actually factor the negative 1 out here. So we can change this to put a negative sign in the front. 2x plus 3 remains 2x plus 3, but the negative 2 minus x actually becomes x plus 2. Right? If you just factor out the negative 1, then it becomes x plus 2. Then we can actually cross out x plus 2. So this one we would have both. Okay, both whole and vertical asymptote. Okay. Okay, so now we actually need to figure out where. Okay, so then in that case, for the whole, it's going to be at 2, comma. Now I need to plug in 2 into x, which I think I actually get a 0. So the whole is occurred at 2, comma 0, right? If you plug in 2 into x, you actually get a 2 minus 2 there. Divided by 2, that gives you 0. This is just a vertical asymptote at x equals to 2. This one you have both, so you have VA x equals negative 3 over 2. That came from there, right? Because that will make that bracket 0. The whole occurs at negative 2. Now what we need to do is plug in negative 2 into x, and if you do that, I believe you get, that's negative 5, negative 5. Yes, negative 5. Okay, so negative 2, negative 5 would be where the hole is. So again, to get this y value, what you need to do is plug in this x value into here and here. And whatever you get would be the y coordinate of the hole. And if you plug in negative 2 here, that gives you negative 5. Plug in negative 2 here, you get negative 1. But it's negative of negative 1, so it's positive 1. So we end up with negative 5 divided by positive 1. That's how I got my y coordinate of negative 5 right here. Okay, so here are 4 questions for you to practice. I will pause the video. No, you should pause the video and then see what you get. Okay, so part A or part D, I guess this is a linear function, so we actually don't have vertical asymptote or holes. It's just a straight line, so there's none here. Okay, for E, you should always factor first. Okay, so you should get 2 times r squared plus 1, which you cannot, I mean, first of all, we cannot factor r squared plus 1. So there's nothing for us to cross out. Okay, so there's no hole. Also, in this case, r squared plus 1 will never be 0. It's always positive. So there is also no vertical asymptote as well. Okay, so this one is actually none as well. Part F, again, you should factor first. In the numerator, you should actually get x plus 1 squared. And over x minus 1, x plus 2, you can see there's nothing you can cancel out. So you would actually end up with 2 vertical asymptotes, x equals to 1 and negative 2. So these are your vertical asymptotes. For G, there is nothing you can do on the top, okay? So you cannot factor the trinomial on the top. You could, however, factor the denominator. That would be x plus 2 times x plus 8. Again, you cannot reduce anything, okay? So you would just actually end up with vertical asymptotes of -8 and -2, okay? So again, there's nothing for you to reduce. In that case, both are just vertical asymptotes. If you can actually factor, then you end up with holes. Oh, sorry, if you can cancel, then you end up with holes, okay? So that's how you determine whether you have vertical asymptotes or holes or not, okay? Now we're going to move on, and we are going to look at horizontal and oblique asymptotes. Horizontal asymptote, I think we've seen that before. It's an imaginary horizontal line, that the graph does not cross. Okay, here's a key, at either ends. Okay, so what I mean by that is on the very left, the graph will not go through the horizontal asymptote. On the right, okay, as you continue to go to the right, the graph will not crosses the horizontal asymptote. You'll get closer and closer to it. Okay, so again, going to the left or going to the right, the graph will get closer and closer to this horizontal asymptote, but it will not cross. However, there are cases that the graph will actually go through horizontal asymptote in the middle. So the key thing that you need to keep in mind is that when we talk about horizontal asymptote, we are actually looking at the end behavior. So this is, okay, so think of end behavior, okay? And behavior. Okay, so it's just looking at the very right and the very left, okay, not in the middle, because in the middle the graph could actually go through horizontal asymptote. It's definitely possible. It doesn't happen very often, but it could, okay? Oblique, sometimes we call this the slant asymptote. I always call it slant asymptote, okay? So, but you'll hear both terms, okay? Slant asymptotes, it's an asymptote, but this time it's not a vertical line or horizontal line. This is a, well, if it's called slant asymptote, it's a slanted line, okay? So it's just like a linear function, but it's a but it behaves like an asymptote. So the graph will go towards this slanted line, but not touch, okay? So this is imaginary slanted line that the graph does not cross at either ends. Okay, so same thing, same as the asymptotes. Okay, but it will get horizontal asymptote. It'll get closer and closer to this slant line, but it will not touch. Okay, so these are another two kinds of asymptotes. So really, we are looking at vertical, horizontal, and slant asymptote here. Okay, so now how can we tell? So let's say again our r of x, that's the rational function, is equal to f of x divided by g of x. We are going to let f of x be like that. So again, this is simply just a polynomial function. Okay, it looks really long, but this is simply a polynomial function. So is g. Okay, they are just both polynomial functions. And let's say in this case, so for f, the degree of f of x, hopefully you recall, the degree of a polynomial function is the highest degree of the biggest power, I guess, you have. Okay, so in this case it's n, right? That is the biggest exponent that we can have. The degree for the denominator in this case is m, right? That's right there. That's the biggest exponent you can have, so that's m. That's the degree of g. So to tell whether we have horizontal asymptote or slant asymptote, it depends on the degree of the polynomial functions. Okay, so here we have, I'm just gonna use r of x to stay consistent. Okay, let's say we have, there's no common factors. Okay, so there's no reducing, there's no canceling, there's nothing happening. It's just two different functions have no common factors. So if m is greater than n, so that is if the degree on in the denominator is greater than the degree on the numerator, then this rational function r of x would have, so for example, it would be something like this. So let's say we have 2x cubed plus 5. and we have, let's say, x minus 2, something like that. You can see when the degree in the denominator is greater than the degree on the top in the numerator. In this case, we would have a horizontal asymptote. And the equation would be y equal to 0, okay? And why is this the case? Well, if you think about this actually makes quite a lot of sense. X cubed outgrows x by a lot, right? If x is 1000, this value will be relatively small compared to that, like actually quite a bit smaller, right? 1000 minus 2, sure, it's 998. But 1000 cubed, that's a big number. That's like 10 million times 2, it's 20 million plus 5, right? That's a huge number. Huge numbers. So is it 10 million or 1 million? 6 zeros. Oh no, 1009 zeros. Oh my goodness, it's like billion. Okay, so again, that is much bigger than the numerator. And if you think about it, a small number divided by a big number, it's going to become very close to 0. And that's why the asymptote is at 0, right? It's going towards 0. Okay, so that's the example if the numerator in the, if the degree in the denominator is greater than the ones in the numerator. Okay, in the second case, what if the degrees are the same for both numerator and denominator? In that case, this rational function would actually have, again, horizontal asymptote. And the equation in this case is going to be y equals an divided by bn. So the constants divided by each other, you can see it's an divided, bm, sorry. An divided by bm. Okay, so they are just the quotient of the leading coefficients. Okay, for example, let's say we have 4x squared plus 5, and then this is let's say 2x squared minus 1, something like that. So in this case, we would have horizontal asymptote at y equals to 4 divided by 2 or 2. Okay, so it's just the leading coefficient divided by each other. And this also makes sense because if you think about it, if x is huge, let's say x is million, 4 times a million squared is, I don't know, a big number, okay? So plus 5. And you can see that plus 5 really means nothing, right, compared to that big, huge number. When you divide that by 2 times a million squared, again, a big number, minus 1. And again, this minus 1 really means nothing. So really what happened is we are actually just looking at this portion. When we have 4 times a million squared divided by 2 times a million squared. And really, x squared and x squared just cancel out. That's why horizontal asymptote is 4 divided by 2, right? Because the graph will actually go towards 2. Okay, because the plus 5 and the minus 1, they are so small, it's really not significant anymore. Okay, of course, it's not exactly 2, but it's going to get really close to 2. Okay. All right, last one, third scenario. If n is equal to m plus 1, so in that case, so for example, r of x equal to something like, let's say, 3x squared minus 1 divided by, let's say, 2x. Okay, so in that case, we would have a slant asymptote. Okay, we would have the slant asymptote. So when the degree in the numerator is 1 greater than 1 in the denominator, in that case, we would have a slant asymptote. Now the question is, how do we find out the equation of this slant asymptote? Remember, slant asymptote is just a line, right? It's an imaginary slanted line. So to find out the equation, what we need to do is we do synthetic division. Synthetic division. Okay, hopefully you remember. That's okay. If you don't, I will show you how to get it in the example down here. Okay. I kind of ran out of room, so I will not show you the example for the one I just showed you. But it would have the form of that. Okay, when the degree is 1 bigger on the top compared to the denominator. Okay. So here are 3 examples. Let's take a look. Part A. This is going to be, well, if you look at the highest exponent, that's this term and that's this term. Both have degree of 2. In that case, we would have horizontal asymptote. And the equation for that is the leading coefficient divided by each other. 5 divided by -7. So be careful, you got to take this negative sign into consideration, okay? It's not just 7, it's -7. Part B, this is in the case of when the degree is 1 bigger on the top, right? That's x squared, that's just x. So in this case, we would have a slant asymptote. And like I said, to find a slant asymptote, all you need to do is do synthetic division. It's 1, 6, -7. Divided by x plus 2, so -2. Now, here's the thing. If synthetic division doesn't work, because I mean, this does not always have to be x plus 2, right? It could also be, this could be like cubic functions in the denominator, which we cannot use synthetic division. You know what? Okay, never mind. I will not use synthetic division. Let me just say long division in that case. Okay, because long division will always work, right? Synthetic division only kind of works if the denominator is a binomial and linear, and it's a linear function, right? Okay, anyways, if you do it by long division, it will always work. So x times x will give you x squared plus 2x minus them 4x minus 7, so times 4, so plus 4, 4x plus 8, the remainder is -15. So the slant asymptote, I guess you can guess that maybe it's y equals to x plus 4. Okay, so that would be the slant asymptote. So the quotient of the division here will become the slant asymptote. Okay. Finally, part C, you can see the degree in the denominator is 10, the degree is 2 on the top. Get clearly bigger in the denominator, so in this case, you would have horizontal asymptote and the equation is y equal to 0. Okay, so these are 3 examples. In the denominator here, it says the equation for the oblique asymptote or slant asymptote is the quotient in the division statement. Okay, so again, you can use synthetic division if you're dividing by a binomial like that, x plus 2 or x minus 1, things like that. But if it's not just x plus 2, if it's like 3x squared plus 5, you know, that kind of things, it's not just linear. In that case, you have to use long division. Okay, so here are 3 questions for you to practice. Pause the video, try it. Okay, so this one, if you actually expand this, you end up with 2x squared on the top. Okay, and blah, 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 doesn't matter. Here you still have the 3x squared, blah, blah, blah. And you can see degree is the same, therefore horizontal asymptote, and y equals 2 over 3. Okay, the leading coefficient divided by each other. Part B, clearly horizontal asymptote, y equal to 0 because the denominator has a higher degree. Part C, this is going to be a slant asymptote. You just need to quickly do a long division. This is going to be x cubed. So you times by 2x. You get 2x to the power 4. And you get 3x minus 4, which there's nothing you can multiply to make x cubed to be 3x. Therefore, the slant asymptote is just y equals 2x. Okay? All right, hopefully you did okay. So that's how we figure out if and where we have our slant and horizontal asymptotes. Okay, so now we're gonna actually do like a summary. Okay, so we're gonna look at one particular function and then we're gonna write down everything that there is. Okay, so I'll do the first one, I'll let you try the other 2. Okay. So we have f of x equals to 2 over x minus 3. So the restricted value of x is 3, right? Because otherwise it's going to be 0, and you cannot divide by 0. So domain, x cannot be 3, right? That's the restricted value, but it could be anything else. Range, well, in this case, we are going to end up with a vertical asymptote at 3. Range, do I want to ask you range actually? Yeah, maybe not. Okay, maybe not. I think some of these examples might have difficult range to figure out. You know what? I'm not gonna ask you for the range. Okay, I'm just gonna ask you for the domain. Okay, so for the whole here, or there's none, right? Because there's nothing we can cancel out here. We do not have a slant asymptote. However, we do have a horizontal asymptote. That is y equal to 0. Okay. Okay. Yeah, in this case, the range is going to be everything except 0. That's okay. I'm not too worried about range. Okay, sometimes it's going to be difficult to figure out. Okay, vertical asymptote, we do have one. Okay, it is x equals to 3, because we cancel anything out. Okay, x and y-intercept. Recall, to find x-intercept, what you do is you make y 0. Now you can see we actually cannot have y equal to 0 because we have the horizontal asymptote right there. Okay, so we don't have any x-intercept. However, we do have y-intercept. Y-intercept is found by making x equal to 0. So you have f of 0 equals 2 divided by 0 minus 3, which is 2 over negative 3. So your y-intercept is 0 comma negative 2 over 3. Okay, so don't worry about the range. Just figure out the domain and then try the other 2 questions down here. Okay, obviously you can graph it on decimals and then figure out the range, but again, I'm not too worried about the range right now. Okay, go ahead. Okay, so this video is going to be long if I don't give you the answer right now and going over the whole thing. I'm just going to quickly read it over. Okay, so restricted value is -4. You can see denominator cannot equal 0. Hence, the domain cannot equal to -4, but everything else. The holes, there's none because there's nothing for us to cancel out. There is going to be horizontal asymptote because the degrees are the same on both top and bottom. Therefore, it's just going to be the leading coefficient divided by each other. So -1 divided by 1, which is -1. X and y-intercept is found by putting 0 into x. So you get 0 comma 1/2. X-intercept is one that we didn't have before. So to find x-intercept is to make y 0. Now, since it's a rational function, to have y equal to 0, what really has to happen is the denominator has to equal to 0. Sorry, the numerator has to equal to 0. So if x is 2, we get negative of 2 plus 2, which is 0. And it does not really matter what the denominator is. As long as the numerator is 0, 0 divided by anything is 0. Okay, so when you looking for x-intercept, just look for the numerator and then make it 0 for that. In this case, range actually could be found. Well, not as intuitive as well, but this one is not too bad. Range, really, y just cannot equal to the horizontal asymptote, -1, and it could be anything else. Okay, so again, these 2 are not too bad because it's just horizontal asymptotes. The third case, in this case, the range really cannot be found unless you take calculus because of the horizontal, because we actually have slant asymptote in this case. Okay, we actually have a slant asymptote in this case. So you could actually plug this into decimals and see what it looks like. It actually looks quite different than the previous 2 that we have. Okay, anyways, this one, we can actually cancel x minus 3. Therefore, we would have a hole. You can see, and the restricted values are 3 and -4. That remains the same, whatever makes the denominator 0. Hence, that's our domain. We could not, the domain x can equal to 3 or -4, but it could be anything else. Again, I'm not going to ask for range in this case because it's not easy. It's not intuitive to get. Okay, holes. Again, to find a hole, once we know they cancel out the x minus 3s, we know the x coordinate is going to be a 3. The y coordinate is simply plugging 3 into the x's. For the remainder of the function, I believe you get -10 out of 7. Vertical asymptote is the one that remains after you cross out things. So x equals to -4. We have a slant asymptote. You need to do long division here. You should get x minus 7. And same thing for x and y-intercept. For x-intercept, make y 0. And yeah, that's right, make y 0. And for y-intercept, making x 0 to find the y-intercept. Okay? Hopefully you got these 2. Now we are going backwards. Okay, so what if we have these conditions and we are trying to write a rational function? Okay, so let's try to do this. R of x. So it says when x equal to 3, there's a hole. Okay, so this means we have x minus 3 and x minus 3, both top and bottom. We have a vertical asymptote when x is -2. That means we have x plus 2 here, but nothing on the top. Okay. Finally is that, well, I should say not nothing, but we don't have x plus 2 on the numerator. Finally says the equation of the horizontal asymptote is -1. So the horizontal asymptote is not 0, which means they have the same degree. And if they have the same degree, then we just take the leading coefficient divided by each other. Now, first of all, they don't have the same degree right now, and therefore I need another x. Now, let's say I just put x plus 5, okay, something like this. But then we want the equation to be -1, which means the leading coefficient, when you divide them together, has to be -1. So all I have to do is put a negative sign in the front. There you go. It's going to be x squared, but negative, so negative x squared divided by x squared, which is -1. Okay, so that's done. So I will do one more, and I'll try the last one. Okay, so r of x, the rational function, f of x, doesn't matter what you call it, okay? When x equals to 4, there's a hole. So I'm going to put x minus 4 here and x minus 4 here. There are vertical asymptotes when x equals to -2 and +2. So we have x minus 2 and x plus 2. And it also says we have a slant asymptote, which means that the degree in the numerator should be 1 greater than the one in the denominator. So denominator, degree 3, therefore on the top we need a degree 4. So the easiest way to do this, well, that's x already, so I need an x cubed here. So I'm just going to make it something like this. Yeah, so just to make sure that they don't factor or anything. Okay, so there you go. That's x to the power 4 divided by x cubed. So there we're going to have a slant asymptote. Okay, I'm going to pause the video and you should try the last one on your own. Okay, so the last one, hopefully you finished it. It says x equal to 2 and x equals to 4. They are wholes, therefore x minus 2, x minus 2, x minus 4, x minus 4. Vertical asymptote when x equals to -3, so x plus 3 here. The equation of the horizontal asymptote is y equal to 0. Perfect. That means the degree in the denominator is 1, or it's greater than the one on the top. We already have that. Done. Okay, that's it. All right, obviously these are just possible solutions. You could have different answers. That is definitely possible, okay? As long as they fit these criteria, it's all good. All right, so finally, actually not finally yet. We have 2 more things to do. This one, it says, is x minus 1 times 2x minus 3 divided by x minus 1 the same as 2x minus 3? The answer is no. Okay, they are not exactly the same. They are almost the same, but not the same. And the only thing that's different between these two is that in this, when you graph it, you actually end up with a hole. In this, you don't. This is just a straight line. So this is a line on the left. This is a line with a hole. Okay, this is just a line, and this is just a line. Okay, so they are different. Not exactly the same, almost the same, but not exactly the same, okay? So be careful. All right, so lastly, I guess it's true or false. Which one of these are rational functions? This one is a rational function. Remember, as long as it's a fraction form and they are polynomials on both top and bottom. Remember, this can be written as 2/1. 2 and 1 are both polynomials, okay? This is also a rational function, okay, because x plus root 2 is a linear function. I mean, you see the square root, but that's only square root for the 2, not the x. So this one's fine. This one is also fine. Okay, this is a quadratic function divided by a linear function. This is fine. That's just simply a quadratic function. This one's not okay. That's a root function, not a polynomial function. Same as this, not okay. This one is okay. This one is also okay. Okay. That's it. Hopefully you're okay with this lesson. Make sure you understand how to figure out all the information for the function, okay? Because next lesson, we are going to take all the information that we can gather and we're going to translate that into a graph, okay? So you need to make sure you understand this so then we can, proceed to the next lesson with ease, okay? Because we are going to graph using the information. All right. Good luck, everyone.